which is then converted to static pressure, and it continues to rise as it passes from impeller to impeller to impeller. This one's horizontally split. This is a barrel pump for very high pressures. Same thing, the hydrodynamic section is a bundle that sits inside the pump. The casing is the pressure containing part, and then you have a head that holds everything together and holds the axial thrust, and some very large bolts that hold this head in place because there's a tremendous force trying to blow the head off. This is a typical performance curve that we might see for a pump system. You have flow versus head in feet. You'll notice that there are lines of impeller diameter, and what that does is it tells you for a certain pump model the range of diameters of the impeller that can fit inside that pump casing. You have lines of constant efficiency, so you can see that when you're where you're operating, you can judge what the efficiency level is going to be. Lines of constant horsepower, and then an NPSH curve, which lets you know what pressure we need in the impeller eye to keep cavitation from occurring. Here's a system head curve. This is what the piping system and the process requirements are going to be for the different pressures. And so on this pump, you would probably have an operating point someplace here where you're at a relatively high efficiency, and you still have some room for adjustment on the diameter if you need to in the future. This is the hot glycol pump we're getting for the GPP project. Very similar curve. It has power on this axis instead of NPSH. The NPSH is down here. But it gives you the minimum and the maximum impeller diameter that will fit inside that casing, and then it tells you which one the pump is going to be built with. And when we buy a pump, we would always have a minimum of 5% margin between the maximum or the minimum and the one that's actually going to be constructed with. Now the reason we do that is if it turns out that the process changes and needs a little bit more head between the time that we place the order and the time that the pump is going to be shipped, or if it's anticipated in the future the head might increase, this gives us the ability to just change the impeller out and get the additional head required for the process. Also, if it turns out that something happened with the calculations when they made the initial selection and it turns out that the impeller doesn't generate head as well as it can, they can, by putting in just a larger impeller, go ahead and meet our process requirements without having to go out and generate or build a brand new pump, which would have to physically be larger and then wouldn't fit inside the footprint or the piping spacing that we had set up. Well, we talk about head a lot, so let's calculate the head of a pump. And the head of a pump is the equivalent column height of water at a specific gravity of 1.0, so that's fresh water. It's equal to the pressure rise across the pump. Now, a water column of 33.96 feet equals 1 atmosphere, so you have a conversion of 3396 by 14.7, 2.31 foot of head for every PSI. That's a real important number for us. So that means that if you had a pump that you wanted to go from 361 PSI up to 789 PSI, it would have to have 990 foot of head. Okay, generally our pump impellers are good for 8 to 1200 foot of head, so this would be a single stage overhung pump. You can see you can get some pretty decent pressure rise out of a single wheel. Horsepower. Horsepower is head times the mass flow divided by 33,000 times the efficiency. So using the head that we just calculated, and a flow of 17,363 pounds per minute, and an efficiency of 84.2%, which is not unreasonable for a decent centrifugal pump, we come up with 618 horsepower. So that's a pretty good-sized pump. But you remember last class we were going to compress gas from 361 to 789 at 1,700, pounds per minute. We need a 33,000 foot head to do that. And here we only need 989. And for us to do the horsepower, it took 20,000 horsepower to make that mass flow go. So for a pump, given the exact same suction and discharge conditions, the exact same efficiency, and the exact same mass flow rate, the head required is extremely small compared to the compressor, and for that reason the power required is extremely small compared to a compressor. And that's why it's a whole lot cheaper to move fluid, move liquids around than it is to move a gas around. Cavitation. Okay, well, every liquid has a vapor pressure. Flash point. I may be erroneously using the term boiling point. I guess the proper term is flash point, and that is temperature dependent. As pressure drops from above to below the vapor pressure, a liquid will flash, causing a significant change in the volume of that mass of fluid. And as the pressure decreases from below to above the vapor pressure, the vapor will condense back into a liquid. Pretty straightforward stuff. What does that mean to a pump? Well, for a pump, you have liquid coming in and it's suddenly being accelerated through the impeller. Well, that sudden acceleration causes a localized static pressure drop. If the static pressure drop goes below the vapor pressure of the fluid, you will end up having a vapor bubble form within the inlet to the impeller. And as the fluid moves further out the impeller and static pressure starts to go back up again, it will then collapse. And you can see it on flow visualization test rigs, which test model, or in some cases full-size impellers, or in this case a propeller for a ship. And you can see where these localized vapor bubbles are starting to form across both the front and the back side of this blade. So why do we care? Well, as that vapor bubble collapses, it goes from a very large area to a very, very small area. And when it finally collapses up against the edge of the impeller, that very small area of collapse causes a very high localized stress on the surface of the impeller, which causes pitting. And if it goes on long enough, you end up having a severe amount of pitting on the impeller and any other place the cavitation occurs. Obviously, since our hydraulic passageway is no longer smooth and we no longer are going to have laminar flow, we are going to increase the losses inside the pump, and so the pump will not be as efficient as it originally had been. It doesn't just happen on pumps. This is the impeller out of a jet ski, and you can see where cavitation pitting has happened on the outboard edge and at the hub, and there's a crazing area right here where it's not the bright shiny metal that it normally is. That's because the cavitation had been not as severe, but it had been taking place clean across the impeller, and it was starting to work on eroding the surface here. If it goes on long enough and it's severe long enough, you end up with the potential for a mechanical failure. So how do we avoid cavitation? Well, we want sufficient margin between the NPSH available from the process and the NPSHR required by the pump. We get that by the proper system design. Sometimes we get it by supply vessel height, or the supply vessel pressure, fluid temperatures, pump selection, proper piping layout, maybe even a different pump style. Yeah.
You said this happens because of the mechanical impact of the bubble?
It's the pressure over area as this vapor bubble collapses, and at the moment that it collapses back into a liquid, it imparts a very large, well, a relatively small force, but it's over an extremely small area, so the stress is extremely high. And the Hertzian contact stress levels are what define if we're going to have material erosion or not. And so if you exceed those stress levels, then you start to have pitting effects on the metal.
This happens in all the systems or only in oxygen-rich systems?
It'll happen in any fluid It can happen in any fluid. We design our systems away from that so it won't happen, but it has the potential to happen everywhere, wherever there's a liquid. It doesn't have to be gas-rich or oxygen-rich because it's not an entrained gas that is forming. It is, if it was water, it's actually steam that's being formed. Yeah.
So pumps that have different NPSH requirements, is that a function of that localized pressure drop where we have the acceleration?
Different pump designs and styles have different NPSH requirements, and that's a function of the geometry of the impeller and the geometry of the inlet, and it's a function of the geometry of the pump.
So it is a function of that localized pressure drop
Yeah.
then? Okay.
Yeah. Yeah.
It's more important for those centrifugal pump. If you're talking about different kind of pump, like a positive displacement pump, are you very concerned with NPSH?
We're not so concerned with NPSH because you don't have a continuous potential for vapor formation, but we are concerned with an acceleration-deceleration head because of the pulsation that reciprocating pumps put into the pumpage. You have a situation where you don't have a nice continuous flow into the pump. It's going to pull stuff, and then it's going to stop, so you have this massive fluid suddenly accelerating as the piston pulls it in, and then it stops when the piston stops. And then next time you pull it in, you have to accelerate it back up again. So if you exceed the vapor pressure, if you drop below the vapor pressure locally when you're trying to accel the fluid inside the pipe, you could have vapor forming at that location. But as soon as that piston stops, that's going to collapse and become a solid, or become a vaporless liquid again. And that'll happen all different places. So if there's any kind of pitting, it'll be spread out over a huge area. So it's not localized like this is. So you don't have the same potential for mechanical failure like you do have in a pump impeller.
If you have an installation, you already have the pump, you have all the piping there. You do know if cavitation. How do you overcome that situation? You have to change the pump, or you can change the piping, or change the process?
Well, there's a couple of alternatives, and we'll talk about that in a few minutes. But you're right. We could possibly change the piping. If you jump to a larger pipe size and you have less friction loss in the pipe, okay, then you'll have higher pressure at the pump suction.
Yeah, but the pressure is the H rho G, but that's suction. So your installation is much more complicated.
Well, you'll find as we go through the next couple slides that the velocity loss of the pumpage through the pipe is a consideration for the NPSH. Yeah, so you have friction losses in the pipe. Bigger pipe, lower velocities, less friction loss. If you can push your vessel up higher, okay, that adds more static head, which will increase the pressure at the pump.
I don't want to change my static head because that is constant. The installation can change it.
Okay. Well, there's some other alternatives then that we can talk about what we can do. Okay, so this is a document the process generates for us. This is a pump head calc. I hope that looks familiar to somebody in here. And up on the top is, it's the header, and it gives you some process information about what you're doing. It has a very nice sketch showing the basic system and how it's going to operate, and then it goes into some calculations that we'll take a look at. So for this, it identifies the pump tag number and the service and what the fluid is going to be, the pumpage temperature, and specific gravities, viscosity, and then the normal pump flow rate plus a percentage of overcapacity. We always buy them a little bit big, and so the final flow rate, 110 GPM. The suction to the pump comes from a tank, which is 10 feet above grade. The pump center line is 2 foot above grade. This obviously changes from pump to pump. 2 foot's a really good starting assumption, though. It identifies the pipe size that goes to the inlet shown that it's a gravity-fed system. We don't see any jumps, but that's the piping layout guy's job to make sure that doesn't happen. It's a motor-driven pump, and that the control is level control based on a high level to low level inside the drum. The drum is an atmospheric drum, so there's no pressure inside, which will help develop pressure at the pump suction. It's vented off to the flare, which is basically atmospheric, which is why the design pressure is 0 psig. Gives you a size. Off of the discharge, you see a flow element and then a control valve, probably to control the flow because that's part of the process requirements. It shows the high static elevation that the piping is supposed to go to. And this is an interesting feature. It has a minimum flow bypass with a restriction orifice, so it's continually bypassing a certain amount of fluid back to the reservoir to protect the pump. We'll get into pump protection a little bit. Down on the lower section, we have the NPSH calculations. And the first thing you do is take a look at the vessel pressure, which is atmospheric. And then you take a look at the static head of the liquid, which in this case is 10 foot minus 2 foot, that's 8 foot. Now this is the most conservative setup right now in that you don't get any credit for the liquid level that's inside the tank. So we're assuming that we have to be able to pump this tank completely dry, or we're not sure where that level is, so we don't take any credit for it at all. So that means that the liquid head, 8 feet, using the specific gravity, is 2.77 psi. And so you end up 17.47. Now here's your piping losses. And that's the friction loss in that 4-inch line that runs to the suction of the pump. But there's also a strainer. So here's the piping loss calculations. Okay, so that means that at the suction of the pump, you've got the total pressure within the vessel and the head of the vessel minus the piping losses, so you get 16.97 psia. Then you subtract the vapor pressure of the fluid, which is 14.7 because it's an atmospheric vessel, and you end up with the NPSH of 2.27 psi or 6.56 feet of head, NPSHA. There's a couple other things here that are not used for the NPSH calculation. So we've got 6.5 foot of net suction, positive suction head available to us. How much do we need? We need a minimum of 3 foot margin between what's available and what's required. So that means that our pump has to be capable of operating with 3.5 foot of NPSH. So one way of trying to keep the losses down in the suction line is that there's no control valves in that suction line. And while the data sheet didn't show any isolation valves or manual valves, those would be full port valves, so they have the minimum amount of restriction that they can possibly have. So nothing shown in here. So if we wanted to raise the NPSH from 6.5, then what we would end up doing is we'd either try to increase this from 10 foot to something higher. And on small tanks and drums, small vessels, you can do that. And you can do it without too much cost. But if you've got a 300-foot tall tower, you really aren't going to move that up 10 or 15 feet. So there are some physical limitations, but that's the most direct way of increasing the NPSH available to the pump. Another one, like we were talking about, would be to increase the line size to reduce the friction. It's not a tremendous amount of increase, but it's something that can be done if you're kind of on the ragged edge of being in cavitation or not. Something else that can be done is, at this point, if you had a cooler and cool the fluid before it goes into the pump, you'll add a little bit of a pressure drop, but if you can get a significant decrease in the pumpage temperature, that drops the vapor pressure down, which will increase your NPSH available to the pump at that point. So there's an alternative. The other thing is, generally, we try to pick the best hydraulic fit and the highest efficiency that we can get for the service. There's a lot of pump manufacturers out there. They have all kinds of different styles of pumps. We can usually find one that's got a pretty good fit efficiency-wise and flow-wise. But when we have an NPSH problem, we may change our selection to a lower speed pump, which will run less efficiently, but it will meet the NPSH requirements. So this came from Gould's Pump. We buy a lot of things from them. And I picked a point at 160 GPM flow at 100 foot ahead, operating 3,600 RPM. This is model 3196. It's a 1.5 by 3-6 that identifies as 1.5 inlet, 3-inch outlet, and a size 6 impeller. 4.65 inches, square inch impeller eye, and a certain pattern for the impeller. You'll notice the efficiency curve shows that this pump would operate at about 67% efficiency, about 67.25. But the NPSH required is 10 foot. So we couldn't use this pump selection for this application because it exceeds the NPSH by over 4 feet. But if we go same model, same 1.5 by 3 flanges to a size 13 impeller, and increase the eye area and slow it down to 1,800 RPM. When we do 160 GPM at 100 foot ahead, you need right around a little less than 3 foot of NPSH, 2.8 feet. So this pump would work. But of course your efficiencies suffered. Your efficiencies down to 52%, so you've lost 14 percentage points of efficiency. So this will cost more to operate, power-wise, but it'll fit your process constraints. So those are things that we can do to try to get a pump to fit in what we need it to do. Now, if it turns out that there's just no way that we can do anything, we can't raise the vessel, we can't get a slow enough pump, we don't want to put a cooler in because the flow rate's so high, we don't have enough cooling water to be able to cool the pumpage down, what you end up having to do is put in what we call the vertical can pump. And what this does is it sets at grade, the motor's above grade, but you have to dig a great big hole in the ground for the pump to sit in. And it's a can because there's an outer containment shell that contains the fluid. So the pumpage comes in, goes down the containment shell to the pump suction. The pump at the bottom of this shell pumps it up and then out. And on this one, this is what we use when we have boiling fluids that are basically right at the pump suction. You have no alternative. This is about the most expensive pump you can get. It's also about the most expensive installation because you've got a huge pit that you have to build. You also have other operational considerations because you've got this big pit. That, of course, is going to fill up with rainwater and dirt and dust and anything else that might happen to be in the area. So you have to continually clean that out or give provisions for getting things out of there that you don't want inside. So this is what it looks like in operation. Nice big pit, this line. The other thing is it has to be extremely accurately set up so that it sits within the containment shell. If you have it off at any kind of an angle, you end up running into the sidewall. You have to make a lot of adjustments. And they're big. They can be quite big. Since NPSH was, the problem before, they just make the pump as deep as it needs to be able to satisfy the NPSH requirements for the impellers inside the pump, and that's usually between 18 and 25 feet, sometimes longer. So, centrifugal pumps, why we use them? They have a wide range of flow rates, and they have a wide range of discharge pressures. They handle a wide range of pumpages, high efficiencies, easy flow rate control, and they have a low cost because there are so many manufacturers out there. We get a lot of economy of scale and a lot of competition so that we get a very good price for this kind of equipment. The problems with them is that we have NPSH issues at sometimes, usually in the process plants and the downstream plants. That's where they come out the most. But most are not self-priming, and sometimes they require flow protection to keep them outside of a bad operation area. And what happens on a pump, you remember on the compressor, as you got down too far in flow rate, you would go into surge, where the flow would reverse itself and try to go up toward the suction. This has a similar situation in that instead of having a nice laminar flow coming off of the impeller vanes, if you get down too far in flow, it just recirculates inside the impeller. You have very little head rise, but you generate a tremendous amount of heat and a tremendous amount of vibration inside the pump. And if you operate there for very long, you end up burning your seals out. So minimum flow protection, let's say we have our nice installation where we've got a tank feeding the pump suction, pumping it someplace else. The best way to protect the pump is to have the pump size so that your process will never go so low in flow that it would go beyond the minimum flow of the pump. But if you can't design your process to do that, then you end up with a flow element and then a recycle valve that would then just continually have fluid traveling in a big loop to keep the pump operating at the correct location on its performance map. Now one would ask, aren't we putting a lot of heat or generating heat inside of this loop? And the answer is yes, but heat generation inside a pump is not as fast or as great as inside a compressor, and so you can operate like this for great lengths of time without building up a tremendous amount of heat inside your process loop. The other low flow protection device would be just to have a restriction orifice, which is a continuously flowing device. So if you wanted to have 100 gallon per minute going forward for your process, if you size the restriction orifice so that it always keeps the pump at least 10 GPM, which is the minimum flow of the pump, you'd have to size the pump for 110 GPM, anticipating 10 going back to the tank and the 100 going forward for your process. It's a nice passive system. You don't have to worry about it operating. It's always there, and unless somebody puts an isolation valve in there sometime, you can always rely on it. Axial flow pumps. This is what they look like. Great big impeller. Looks like a ship's propeller. Fluid comes in, fluid goes out. This is a relatively small one. But what they're good for, very, very high flow rates. Sometimes you'll see them in cooling water systems when you've got steam turbines in the area. Very high efficiencies because of the high flow rate. Really low head, and they're also not self-priming. This is the style that you would not want to use the priming fluid injection on because you've got such a huge pipe that you have to try to flood. Okay. We've been going for an hour. Let's take a break here for 15 minutes and reconvene.